Namaste. Welcome to the lecture series on the subject Applied Thermodynamics. This is module 4 in that part 1 refrigeration cycles. This is lecture number 3. Myself Dr. Nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So in the last two lectures we studied about the ideal vapor compression cycle and we analyzed the various components of ideal vapor compression refrigeration cycle. Now in this lecture first we will discuss about the actual vapor compression refrigeration cycle. So as all of you can see in the pH chart, there is some changes in the compression and the expansion process when compared to the ideal cycle. So as I told earlier, so the compression process, the point 1, if it is on the saturated vapor line, and the point 2, see, after compression automatically it has to go to the superheated region if the initial state 1 is in the dry saturated region or line. Now this compression process is called as the dry compression. Now in actual compression process, so there is a bit of superheating at point 1. That means the refrigerant which enters into the compressor is not dry saturated, instead it will be a bit of superheated, so that the temperature 2 dash, that is point 2 dash, will be still highly superheated when it enters into the condenser. So this is one of the changes when compared to the ideal vapor compression cycle. And also now look into point 3. So in the ideal vapor compression cycle, I told you that the point 3 will be in the saturated liquid line. Now you can see in the actual vapor compression cycle, so there will be a bit of undercooling to point 3 dash. So now 3 dash to 4 dash is the actual expansion, whereas 1 dash to 2 dash is the actual compression. Now let me discuss why these changes. So keep these pH chart in your mind when I go to the next slide. The first point, a constant amount of superheating of the vapor before it enters the compressor is recommended. So that is what I told you in the previous slide using pH chart. So why? This is to ensure that no liquid refrigerant droplets enters the compressor, because compression of vapor is easier and compression of the liquid, suppose if there are some liquid droplets entering in the compressor, then compression process will be a problem. So a small degree of subcooling, so that is point 3 dash, 3 to 3 dash is the subcooling, 2 to 2 dash, sorry, 1 to 1 dash is the superheating. So a small degree of subcooling, that is undercooling of the liquid refrigerant at the end condenser exit, is desirable. Why? In order to reduce the mass of vapor formed during expansion, because earlier we studied that during expansion, so there is a possibility that a small amount of vapor may be formed. So what happens if the vapors are formed? So excessive formation of vapor bubbles may obstruct the flow of liquid refrigerant through the expansion valve. So in order to avoid this, so we have to ensure that there will be some degree of undercooling before the liquid refrigerant exits the condenser or enters the expansion valve. So both the superheating at the evaporator outlet and the subcooling at the condenser outlet contribute to an increasing refrigerating effect. So there will be, you can see the increase in the length of the line, that is 4 dash to 1 dash. So more amount of heat will be absorbed from the space to be cooled, hence there will be increase in the refrigerating effect. However, the load on the condenser also increases. You can see instead of heat being removed or rejected to the atmosphere from 2 to 3, now it will be from 2 dash to 3 dash. So there is an increase in the amount of heat rejected to the atmosphere. So there will be some increase in load on the condenser. There will be an increase in the compressor discharge temperature also. You can see the point 2 dash. So 2 dash is going towards left of the superheated, right of the superheated region. So more it moves to the right of in the superheated region. So there will be an increase in the temperature of the discharge temperature of the compressor. That means the vapor temperature will be high at the exit of the compressor. Since the compressor input more or less remains unchanged, so there will not be much change in the work input required for the compressor, the COP of the cycle appears to increase due to this superheating and subcooling. So the ultimate effect on the performance is the increase in the COP. However, for a fixed temperature of the refrigerated space, the evaporation temperature must be lowered. So for a fixed temperature of the refrigerated space, the evaporation temperature, the temperature at evaporation is taking place, that T evaporation gets reduced because of this subcooling and the superheating. Further, for a fixed temperature of the cooling media, the condensation temperature must be raised. So T condensation will be higher, so hence COP will reduce. Now let us discuss about the refrigerants and their desirable properties. The most commonly used refrigerants are the group of halogenated hydrocarbons marketed under various proprietary names of freon, genetron, arctron, etc. So these are the commercial names. You see, freon, genetron, arctron, all these things are the commercial names of the various refrigerants. They are nothing but a group of halogenated hydrocarbons. Among them, freon 22, which is nothing but monochloro-difluoromethane, and freon 11, which is nothing but trichloro-monofluoromethane, and freon 12, which is dichloro-difluoromethane. So they are the most extensively used refrigerants. So one more refrigerant which is commonly used is the ammonia, and in addition to that you can also use CO2, SO2, methyl chloride, then methylene chloride, ethyl chloride, etc. So these are about some of the refrigerants commonly used as in the various refrigerators. Now coming to the desirable properties of the good refrigerant. So these are classified into different categories. Now coming to the thermodynamic properties. So what are the desirable thermodynamic properties of a good refrigerant? So it should have the low boiling point. So the boiling, especially this is for the evaporator, because it should have low boiling point so that it can easily evaporate. So if it, you see, during the evaporation process, the liquid refrigerant should evaporate. If it evaporates, it can absorb more amount of heat, because you know that the latent heat is the more than the specific heat. For example, if I take the water, in order to increase the temperature of 1 degree water by 1 degree, 1 kg of water by 1 degree, so I have to supply the amount of heat which is called a specific heat, which is 4.186 kilojoules per kg. Whereas the latent heat, that is from water, liquid water to water vapor, so it will be around 2200 plus per kg. Just imagine, whereas 2000, this is latent heat of vaporization of water is 2000 plus kilojoules per kg. That means whenever a liquid refrigerant gets evaporated, so it will absorb more amount of heat, or similarly when it is condensed, so it will give out more amount of heat. So that is why the refrigerant should have the low boiling point. Then it should have low freezing point, so that it should not form solid. It should not be become solid during its flow in the various pipelines. And the positive gauge pressure in the condenser and evaporator, but not very high. You know that positive gauge pressure, that means the pressure in the condenser and evaporator should be more than atmosphere, because gauge pressure is the one which uses atmosphere pressure as the reference for the measurement. So in that device, atmosphere pressure is marked as the 0. So positive gauge pressure means you should have a reading above 0. That means the pressure in the condenser and pressure in the evaporator should be more than atmospheric, but not very high. And also it should have high latent heat of vaporization. That's what I told you when I explained about the low boiling point, because here the low boiling point means it can easily evaporate. If it easily evaporates, so it can absorb or liberate that latent heat of vaporization, which is very high. Now coming to the chemical properties, a good refrigerant should be non-toxic and should not catch fire, that is not non-inflammable. It should not be explosive, it should not be corrosive, and chemically stable. That means during its all these phase changes or temperature changes, pressure changes, it should not go any chemical reactions or chemical changes. So chemically it should be stable, and also should not have any effect on the quality of the stored products. That's very, very important. Continuing with the desirable properties, coming to the physical properties, so it should have low specific volume of vapor. So specific volume is volume per unit mass of the substance. So if it has less volume per kg of substance, so it will occupy less space. So easily the mass flow rate of the refrigerant can be increased in a smaller diameter pipe also. And it should have low specific heat. So specific heat should be less. That means less amount of heat should be supplied to increase its temperature, so that from liquid to from a given temperature to its boiling point easily it can reach. So if it is high specific heat, means it requires more heat to reach from the freezing point to the boiling point, right? So every degree rise in temperature, so amount of heat should be heat that should be required should be less. Then we call it as low specific heat. Then high thermal conductivity, it should have high thermal conductivity, and it should have low viscosity, so that easily it can flow through the pipes. Now coming to the other properties, ease of leakage detection. That means should have some smell, so that when there is some smell, if there is any leakage in the system, easily we can find out, and cost should be less, and it should be ease of handling. The cost of the refrigerant should be less and handling should be easier. So this is about the desirable properties of a good refrigerant. Continuing with our discussion about refrigerants, let us discuss about ammonia and the freons. So ammonia is a good refrigerant with the highest refrigerating effect per unit mass. Means for a given mass it can absorb more amount of heat, and also it is relatively cheap, but it is toxic and corrosive. So there are the two drawbacks when we use ammonia as the refrigerant. But advantage is leakage can be easily detected because of its pungent odor. Now when coming to the freons, so they are non-toxic and non-inflammable, means there are advantages when compared to ammonia. Ammonia is toxic, but freons are non-toxic. Here it is non-inflammable. But the disadvantages of freons are leakage cannot be easily detected. That is because they are colorless and the odorless. So what we do is some colored additives are sometimes mixed with the freons to facilitate detection of leakage. So this is the discussion about the various refrigerants. Now with this I conclude this lecture here, and I'll continue further discussion in the lecture number 4. Thank you.